All right, so let's go ahead and get started. So we have our first exam on Thursday, so today's going to be all review. At the beginning, what I'm going to do is I'm going to lay out all of the equations that we're going to see on the exams, or on the exam, and then I'm going to open it up for questions and study hall. So you guys can work on whatever you think is going to be helpful, and then we'll come around and help you, and then we can also answer questions on the board if you have them. Okay. So to start out with, the first equation that we had this semester was Coulomb's law, and what that did was it told us what the force was between two charges. So call this some Q1 and some Q2. And so if I want to find what the force is that Q1 acts on Q2, we said that this force, and we're going to treat this as a magnitude, is going to be equal to K Q1 Q2 over R squared. And then once we found the magnitude of this force, what we could do is we could consider what the signs of these charges are. So when we plug this into this equation, we took an absolute value of the product of the charges. And so if for instance we said this was a plus charge and this was a minus charge, we could calculate what the force is between these if we knew what this distance was and what the magnitude of the charges were. And we can say, well, this is a positive charge and this is a negative charge, so they should attract each other. So the force that charge Q1 acts on Q2 is going to pull it this way. Okay, so that was the first set of things that we talked about. And then after that we said, well, if we have this force between charges, it might be beneficial to think about what could we say imagining there was some charge here. And that led us to the electric field, and so what we said was the electric field from a point charge, E, is going to be equal to KQ divided by R squared, where if we had some positive charge, we had some electric field radiating away from the charge, and if we had some negative charge, then we could say that the electric field goes towards this one, okay? Now, we kind of built this into a table at the end, and so the next equation that we could have is for the potential energy between two charges, and this is just to say that U is going to be equal to K Q1 Q2 over R. And so this tells us in the same sense that if I compress a spring, we know that stores some energy because it has a tendency of, if I let it go, to try to push it back or to pull it back towards equilibrium. If I have these two charges here, they want to either attract or repel each other, and so I hold them here, then there's some tendency for them to want to move, and so that's what we can call the potential energy between the two charges. The last equation was for the electric potential of the point charge. So that's to say that V is going to be equal to KQ divided by R. And so this was analogous to talking about some hills that are formed by these electric potentials. And by now we've done the lab, and so you saw how if I had some plus and some minus charge here, this kind of makes these this hill feature like this. So this would be the electric potential of the positive charge, and this would be the electric potential of the negative charge. And so near positive charges, you have, moving away from the positive charge, you have a decrease in electric potential. Moving towards the negative charge, you have also a decrease in electric potential. So these are only for point charges, but we also talked about what could happen if we wanted to consider general relationships between these, and this is where our table came from. And so if we wanted to say, how do we get from force to electric field, we could say that the force acting on a charge is going to be equal to the charge times the electric field that it's in the presence of. And so what we did with this was we said, well, we don't really care what the charge is that produces the electric field, but imagine I have some constant electric field everywhere. So the example that we had was, we said between the plates of a capacitor, we don't even really care what the charge arrangement is, we just care that we had some electric field here. and then we put the charge in this electric field, and we wanted to see what the force was on it. So we could go vice versa between the two of them. If we want to solve for what the force is on a charge, or we want to know what is the electric field required if I want to have this particular force. Okay. Now we also saw that we could go from the force to the electric potential, or sorry, the electric potential energy. And so that says that this is the electric potential energy. And to go between the two of these, we say that the force in the x direction is going to be equal to the negative change in electric potential energy divided by the change in distance. Okay. Now the relationship between the electric field and the electric potential is much the same way, and so if I wanted to go from the electric field to the electric potential, what we said was that E sub x is going to be equal to minus delta V over delta x. Okay. Now the last relationship that we can put in is the relationship between the electric potential energy and the electric potential, and this is very similar to the one that we had between the force and the electric field. This says that U is going to be equal to Q times V. Okay. So this is probably 3/4 of the exam, just the relationships between these things and how do I calculate the force on charges if I have like a grouping of charge, or if I want to find what the force is given the electric field, or what is the electric field given the electric potential. This is probably maybe a little less than 3/4, at least 2/3 of the exam. The last portion is going to concern circuits, and so what we saw with circuits was that there are kind of these two ways that we could approach circuit analysis if we had the right arrangement. And so the first way, and the camera's not on this one, so I'll keep using this one. The first way is the more general way, and that's to use what are called the Kerkhof rules. And so the first rule is the loop rule. And that was to say that around any closed loop, the sum of the change in electric potential is going to be equal to 0. And the second rule was the rule that said that the current into some junction is going to be equal to the current out of the junction. So I can say the sum of the current in is going to be equal to the sum of the current out of the junction. Okay. Now, the other way that we could do this, if we're fortunate to have a circuit where we can find the equivalent resistance, is to do this analysis by adding the resistors in series and in parallel. And so that's to say that the equivalent resistance in series is going to be equal to the sum of the resistors. And in parallel, 1 over the equivalent resistance is going to be equal to 1 over R1 plus 1 over R2 plus, okay? So in terms of the formatting of the exam, expect at least one, well, exactly one. I'm not going to do more than one Kerkhof loop rule circuit. A circuit that involves adding resistors in series and parallel, and then some combination of the rest of the topics that we have here. So if I have, for instance, some charges, arranged in some particular way, find what the force is here, find what the electric field is here, find what the electric potential energy is. If I have some charge in the presence of an electric field and it moves some distance, what's its velocity after it's gone that distance? Questions like that. We've done quite a few of them. Okay. Any questions about this? Okay. So like I said, we're going to use this time just kind of as a study hall, and so I'll come around and answer whatever questions you guys are working on as you're going through.